All right, welcome back, chemistry people. Today we're going to continue our study of equilibrium, and we are going to explain how systems at equilibrium respond to disturbances by partially countering the effect of the disturbance. As always, let's break this content objective down a bit. First thing we're going to do is define and explain this idea of the reaction quotient labeled Q. Then we're going to define Le Chatelier's principle, and then we're going to use Le Chatelier's principle to predict the direction of the shift resulting from various possible stresses on a system at equilibrium. So what happens, when we add more reactant, or we add more product, or we heat things up, or we increase the pressure or decrease the volume, or basically stress it. And then lastly, we're going to connect Le Chatelier's principle to the comparison of Q to K, so our reaction quotient to our equilibrium constant, by explaining what happens, what are the effects of the stress on those two things. So that is what we are going to do today. So first things first, what is this reaction quotient Q? Basically, the reaction quotient Q is a measure of the proportions of the products to reactants at any point in a chemical reaction. That sounds familiar. Maybe that's because exactly how we define the equilibrium constant K. Oftentimes, however, this is measured using initial concentrations of reactants. So at any time, not necessarily equilibrium. So just like equilibrium constant K, it's going to be the relationship between your products to your reactants. Now, a couple of things to keep in mind as we relate Q to K. If Q is less than K, again, remember K is equilibrium, so if it's less than K, it's not at equilibrium, and product formation is favored. So as you think about this general reaction here, we're just going to, for example, say that at equilibrium there's a lot of products present. And if Q then is less than K at that given point, or at a given point, then it's understood that we are going to have a lot of reactants at that given point that Q was measured. And if Q is less than K, in order to establish equilibrium, we're going to use those reactants up and form the products so that we reach equilibrium. If Q, however, is greater than K, again, we're not at equilibrium because it's not at K, but here we're going to favor the formation of the reactants. Again, just for an example's sake, if our at equilibrium we have a lot of reactants present, that means we have a relatively small K value. And if Q is greater than K, okay, so we're not at equilibrium, but that means that we're going to have a lot of products in comparison to our amount of reactants. And so in order to achieve equilibrium, we're going to drive towards the formation of our reactants so that we reach equilibrium, so that Q becomes K. If you measure and Q is equal to K, then guess what? You are already at equilibrium. So here's a thriller of an example. If K, for example, is large because there's a lot of products at equilibrium, then that means that if you measure Q and it's equal to K, then guess what? You already have, you're already there, and you have the same amount of products compared to the reactants as you do at equilibrium. Now, in your notes, you're given a real thriller of a graph just to illustrate this point and the relationships between Q and K. Notice there you're given just sort of a general reaction of A forming B. Q is just the relationship between your product B and your reactant A. Notice that initially, as you start here, you are going to have all reactant and no product. And here we've got mostly product and no or very little reactant. And equilibrium is established right here. The equilibrium value for this is given to us as 1.45. And so you can just spend some time, your weekends, thrillingly looking through this diagram to understand that relationship. I think with a few moments you'll become very well versed in the reaction quotient Q. So now that we've discussed equilibrium and the equilibrium constant K and the reaction quotient Q and the relationship between the two, briefly, we're going to talk now about Le Chatelier's principle. And Le Chatelier's principle is just something that we use to guide us in predicting the effect of various changes in the conditions on the position of equilibrium. So once we've reached equilibrium and we start to stress things out by adding reactants or adding products or changing the pressure, changing, Le Chatelier is going to sort of guide us and help us understand what's going to happen so that we can sort of minimize that disturbance and reestablish our equilibrium. So stressing the system, keep in mind then, is going to result in different concentrations of pressure. So if you add reactants or if you add products, but recognize your equilibrium constant K is not going to change unless, of course, you have temperature change. So first things to think about when it comes to stresses, we can affect the concentration. So we can add things, take things away. Keep in mind though, this is not going to affect the value of K. Even though you may be adding reactants or adding products, it's going to shift so that the ratio between those two things is going to come back to the original constant value. So in general, keep in mind equilibrium is going to shift away from the side with added chemicals or toward the side with removed chemicals. So if the concentration of the reactants is increased, you add reactants, the result would favor the formation of the products. Again, we're going to sort of shift to form more products so we can kind of counteract that stress and reestablish equilibrium. If the concentration of the products is increased, the result would favor the formation of the reactants. It's going to shift backwards, again, to sort of reestablish equilibrium. So as you take a quick look at the beautiful figure that's in your notes there, you are provided with a graph for this reaction between N2O4 and NO2. Recognize that we add N2O4 and it sort of shifts to form more NO2. So notice our concentration of N, so we put in this N2O4 and then we make more NO2, and as we make that NO2, we use up some of our N2O4. But notice then we sort of reestablish an equilibrium, and although these concentrations are different from what we had originally, the ratio between those two things is going to give us our same equilibrium constant value. Note here, we're now talking about adding the other thing, in this case the NO2, our product. Notice we add the product NO2 right here, and it shifts to form, so this gets used up and we form more of our N2O4. Again, keep in mind that adding those things, adding either reactant or product, will cause it to shift one way or the other so that that equilibrium is reestablished. A couple of things just to keep in mind, or other things to keep in mind when we talk about adding things. Sometimes you will see problems where they talk about adding an inert gas or a gas that's not involved in the equation. So things like helium or neon or things that are just not going to react. And keep in mind they're going to have no effect on the position of the equilibrium because they're not going to affect the partial pressure of the gases. They're not going to take part in the reaction. Okay, so the first thing, again, you need to keep in mind is how the change in concentration will affect equilibrium. You also have to worry about, with gaseous reactants and products, is how will volume or pressure change or affect equilibrium. Again, keep in mind it's not going to change the equilibrium constant K. But keep in mind that when you're trying to figure out how volume or pressure is going to affect equilibrium, you need to first count the number of moles of gas reactants and gas products you have to predict which direction the equilibrium is going to shift, or which the reaction is going to shift. So as you look at the equation in your notes there, we've got the formation of ammonia gas from nitrogen hydrogen gas. Note that on the reactant side of this equilibrium, we've got 4 moles of gases, we've got 1 mole of nitrogen, 3 moles of hydrogen, so 4 moles of gas reactants. But on the product side, we've got just 2 moles here. So it's important to sort of set up, before you begin these types of problems, how many moles of gas reactants, how many moles of gas products, because if your volume is increased, in other words, the pressure decreases, or either way, the system is going to shift to the side with a greater number of gas moles in order to increase the pressure, sort of reestablish that equilibrium. I think this one's easier to look at a little visual for. So as you look at this visual, you've got your decrease in pressure or your increase in volume. The reaction is going to shift to the side where there is a greater number of moles of gas, sort of go back to re-increase the pressure. You've got more moles of gas, so you've got more things sort of knocking around to sort of re-increase the pressure after that increase in volume. It doesn't have to be to the left, it just has to be the side that has the greater number of moles of gas. The reverse of that, so if the volume decreases or you increase the pressure, we're going to shift to the side with the fewer number of gas moles. So we decrease the pressure and again try to re-establish that equilibrium, try to oppose that change, that stress that we put on the system. So here we're going to increase the pressure, and now we're going to shift towards the side that has fewer moles of gas. And again, in so doing, there's less particles knocking around, so the pressure is going to decrease to sort of counteract that increase in pressure, or that decrease in volume that was done. Okay, and the third stressor to keep in mind, and that this is the one that will affect the value of your equilibrium constant K, is the effect of temperature. Now, we need to think first, what is going on with the reaction? Is it endothermic or is it exothermic? So first we're going to take a look at an exothermic reaction. And what's really important with these types of problems when you're trying to figure out how the system is going to respond, it's important to write your heat energy in as a reactant or product, depending on whether it's exothermic or endothermic. So the first example we're going to use is an exothermic reaction. Notice or recall you're going to have negative delta H values. And if it's exothermic, your heat is essentially going to be a product or given off in an exothermic reaction. And so as you look at how we've rewritten that here, we put energy in as a product. And that's going to be very helpful. Always sort of rewrite your thermochemical equation with the energy as a product in this case, or as a reactant in an endothermic reaction. So in an exothermic reaction, as we have here, if you add energy to the system, if you add heat, if you increase the temperature, the result is going to favor the formation of the reactant. So just treat it like it's another reactant or product. So if you're adding energy here, it's going to shift to sort of counteract that. So when in an exothermic reaction, if you're adding heat energy, it's going to shift to form reactants. And if you're forming more reactants, think about where that's at in your equilibrium constant K. It's in the denominator. It's going to give you a smaller equilibrium constant K. If, however, we take heat away, you cool things off, you are going to be pulling this away, and so you're going to be forming more products there. And again, if you're forming more products, think about how that's going to affect your equilibrium constant K. Products are in the numerator, so if you're forming more products there, you're going to increase your equilibrium constant K value. Let's talk endothermic now. Again, keep in mind that when you have an endothermic reaction, you're going to have positive delta H values. Great idea to rewrite your thermochemical equation with the heat energy in the reaction itself. This time, however, notice on the reactant side. So similarly, if we add heat to the system here, this time we're going to add reactant essentially, and it's going to push it towards the formation of the products. Here we're going to get a larger K value, again, just because of where products are located in the equilibrium constant expression. If we take it away, we're going to favor the formation of the reactants. We pull this out, the formation of the reactants are going to be favored. And again, because we're making more reactants, smaller K value there. And then lastly, in terms of disturbing equilibrium, catalysts will not affect or the position of the equilibrium. It's only going to change the speed at which equilibrium is achieved. So if you add a catalyst, it's going to get to equilibrium more quickly. If you don't have a catalyst or use an inhibitor, it's going to get there more slowly.